For mass timber building, I see that this is all a collaborative effort. From the day one, acoustics and vibration need to be involved. We are pushing the boundaries to extend the capabilities up to 2000 MIPS so that mass timber building could be used all sorts of lab buildings.
This time, learn how mass timber floors behave differently than steel or concrete, and find out how innovative modeling methods can optimize performance and make mass timber practical for vibration-sensitive spaces. Join Senior Principal Paul Becker and Vice President Kristina Rogers, both structural engineers based in Portland, Maine, as they talk with Sami Rahman about vibration and acoustics in mass timber.
Hello, everybody, and welcome to another episode of our Mass Timber podcast. I'm Paul Becker, and I'm joined by my colleague, Kristina Rogers. Kristina, how are you today?
I'm great. Looking forward to this discussion. Yeah,
I am too. This is going to be an interesting podcast because today we're going to be talking to Sami Rahman and talking about what we think is maybe one of the most technically challenging and sometimes misunderstood aspects of mass timber design. It's all about vibrations and acoustics. Sami is an acoustic and vibration specialist out of our Mississauga, Ontario office, and he's got expertise in structural dynamics and ambient vibration analysis and acoustic design. So he's been a leading researcher in project applications in the mass timber space. And so we're going to explore how we can improve our design confidence, what the industry still needs to learn, and maybe find out how Thornton Tomasetti is helping set the new standards. So, Sami, welcome to the podcast. How are you?
Thank you. I'm doing good. Thank you for having me.
So maybe to start off, can you share a little bit about your work at TT and what led you to focus on vibration and acoustic performance?
Sure, Kristina. By profession, I'm a structural vibration engineer. I work with vibration design of buildings. This could be based on a pedestrian vibration or could be a train-induced vibration. We work with tune mass jumper, strengthening of the floor framing system, or any types of specific or specialty vibration design for buildings. The dynamic behavior of a mass timber is completely different than typical concrete or steel structure. So when we do the design for a facility where a strict vibration criteria is needed, we know that certain standards or certain protocols have been already established. But for when we start working with mass timbers from 2021, we realized that most of these established guideline is not directly applicable here. So here I become really interested to understand what could be done to improve the performance of mass timber.
So, Sami, you started work as a structural engineer designing buildings initially, right?
Yes. Yeah.
Okay. So you got a great background for this. And then I was curious, how, in your opinion, is the performance or the evaluation of vibrations different in a concrete building, steel building versus a timber building? What are the issues that you're facing, or what are the topics that you have to figure out?
So for a typical concrete building, we have enough mass in the building. It's a beefy structure. The same thing for steel deck structure. It's gonna have some concrete on top of a steel deck, so we have some mass in there. In most cases, concrete and steel building are a low frequency floor, so the vibration is governed by resonance of the floor system. But for mass timber building, this is governed by high frequency response because mass timber doesn't have enough mass in here. So even though there is a mass included in the name, but inherently from vibration point of view, it is actually lightweight.
So it's mass in volume, not mass in weight.
Right.
So as it is a high frequency floor, so the response is significantly different, and the response is governed by impulse response of the floor. So to control this, we need more mass. It could be a thicker CLT floor, or it could be a composite floor to control those excessive motion in the high frequency range. But there is a limit how much concrete we can put on the floor system. So there is a right amount of balance needed between the framing of the mass timber as well as how much of concrete or how much of another system we can include to the mass timber building to control the motion of the floor. So from that perspective, it is really, really challenging, and at the same time, it is interesting.
So we started by talking about how you're an expert in both vibration and acoustics, but I think we wouldn't normally think of them as tied together. Can you explain that a little bit? And does the same issue of the mass apply to the acoustic issues that we see?
Yes, Christina. So what happens for mass timber floor, as we don't have enough weight on the CLT floor panel, so whenever we try to change something from the typical design, like inherently we saw that it impacts the performance of acoustic as well. So to be improving the performance of acoustics, we need a complete separation between a CLT floor and concrete on top of it. But to improve the performance of vibration, at times we need to use special types of composite deck design that would have some nailing done between concrete and CLT floor. So when we do the nailing, we need to be mindful of specific spacing and the type of the material, because based on the extent and the spacing, it could significantly impact the acoustic performance. So here we are improving the vibration performance, but impacting the acoustic performance negatively. That's the unique situation for mass timber building. For concrete and steel structure, we don't have this issue. If we design it for vibration, in almost all the cases, this is good for acoustics. But here we need to be careful.
Yeah.
So when you're balancing vibrations and acoustics, and you're saying you're going to put in some screws into the CLT to connect the topping slab from a vibration perspective, just enough to make the connectivity. What is the decrease in the acoustic performance? Like, how do you gauge what the impact is on the acoustics?
So similar to vibration, we also have an acoustic model. So it's a desktop study at this point. So because what we'll do, we start with the vibration design at first, because in most cases we see that it's a controlling factor. So when we come up with a final solution for vibration, we are going to simulate it in an acoustic software. And then we're going to see that how much of pipe performance is going to be impacted. So for us, acoustic is very important as well. So we need to confirm that it's not being negatively impacted by superior vibration performance.
So would it be somewhat based on the use of the building? Like if you have a laboratory building with microscopes, I would think that the vibration criteria might take priority over acoustic, but that's an owner stipulated thing.
Yes, you are right. So that criteria that we are targeting is going to be based on an internal discussion, mostly from the client or an equipment vendor or the lab specification. We would give them the criteria that we need to achieve. And we'll also have a specific criteria for acoustics. So we are going to start with those criteria and then try to find the sweet spot between acoustics and vibration.
Yeah. So it sounds like you're really walking a tightrope then between getting enough connectivity to improve vibrations and not at the same time hamper acoustics. What, in your experience, and you and I have worked on a recent project, but how do you determine where that sweet spot is?
So the recent project we worked together, it's a university, a Cornell University project. So at first we started with our structural design drawings. We would build a Ferdinand model in a software environment. And the first step would be to simulate the response that would be based on typical guideline limit value, and the typical standard design parameters have been established. But as we discussed, that mass timber is different than concrete and steel structure. So then here is the importance of the field testing comes into play. So we have done a couple of testing there to understand the difference between mass timber building and other type of construction material. And then based on this, we tweaked our design parameters and the modeling parameters to some extent. So our office is in a very unique position right now from that perspective, that we have complete capability of computer simulation, and at the same time we have field data set that we use to calibrate our mass timber modeling parameters. When we do this calibration, after this, we provide the first set of results to the structural engineers that with this kind of structural framing members we need. But in most cases, what comes up happening that because this framing system has to meet some structural restriction as well and architectural limitations, we then take those parameters into effect, and then we modify our design assumptions and then change our modeling parameters to update the results. So the way I see it, actually, it's a back and forth between structural discipline and vibration discipline, and a tight correlation and coordination is needed.
It's interesting because in the structural model, we tend to be more conservative. So there's this like interesting fine tuning of you typically assume more fixity and connections than we do in the pure structural model, right? And then how does the facade impact? How do the finishes impact? I think there's a lot of things that are added in your model, right? That we're not
Uh,
considering in ours.
Yes, Christina. So most importantly, the biggest change between structural model, the vibration model, is how we design the connectivity, and
Hmm.
how do we consider the stiffness effect of non-load bearing partition. It could be an internal partition or it could be an exterior facade element. Because from vibration point of view, where the serviceability load point is the most crucial factor. The issue is actually if we don't consider the impact of the partition wall or don't consider the fixity under the small magnitude loading, it will come up with a very significant requirement for structural engineers to know that deeper members, thicker concrete slab, or like a thicker CLT panel. That is not appropriate in this case because when we are looking into vibration design, as you rightfully pointed out, it is going to be other end of the design. We want to have some conservatism, but at the same time, we would like to mimic the real world scenario. Like when someone is walking on the floor, the loading is too small, and even there is a hinge support from a structural point of view. For vibration, it's going to be modeled as a fixed support because under small loading, the
Yeah.
joint is going to act as fixed support. So this kind of tweaking and parametric modeling update we need to do to have a realistic vibration results from our model.
So during the design of the project at Cornell, we did this back and forth where we kind of fine tuned the stiffness of things and we made certain assumptions about interior partitions, facades, etc. We had an opportunity to go in there and do some testing, and you were able to calibrate our guesses at stiffness with the reality of stiffness that we were seeing based on that testing. Can you talk to us a little bit more about that? I find that really interesting.
Yes, that was an interesting project for us as well because the unique of this project was we're trying to achieve 4,000 MIPS. That's actually very common to achieve by a concrete structure and a steel deck structure.
Yep.
But to achieve this with a mass timber floor, it is, I would say, very few construction is like this. So we did some estimation, we did some modeling parameters, we did some estimate on our end at first, and then there was a coordination between structural team and the and our vibration team to find the right depth and right thickness of the CLT. So when we're on site, we were really lucky in that situation that we can go back and do a follow-up testing how the structure, as built structure, is behaving, and just to confirm our assumption at this point. So we did heel drop testing, we did impulse response testing, and then walk testing on the floor, as well as we looked into the stiffness calculation of the wall partition. So based on our assessment, the good correlation between our prediction results and field measurements. And we see that some tweaking that we have done based on our past measurement, it is a good correlation on this site assessment as well. So it was our confirmation that the modeling technique that we are using and the modeling parameter that we are choosing, it is actually performing, and our understanding is solidified that we are on the right track to take this modeling into the next level.
So, Sami, I assume that having the opportunity to go back at completed structure and do the testing is super valuable. Are you actively pursuing this with other projects to build a database to help us better predict performance?
Yes, we would like to take every opportunity to collect those data sets. The main reason is these modeling parameters that we are choosing for mass timber building. In most cases, those recommendations were given based on lots of steel deck construction. And we would like to confirm that these parameters, specifically those stiffness of the internal partition wall and the exterior facade wall, how accurate these are. So far, what we are observing on site is these parameters need to be updated because in mass timber floor, the stiffness of those elements plays a significant role. And recently, we have been using those parameters or tweaking parameters to achieve higher performance with a mass timber floor. If we don't use these parameters effectively, then we would need a thicker concrete on top of the CLT, or maybe a more, tightly spaced spacing of the nails, that is not economical. And as I mentioned, it will have a negative impact on the acoustics. So we would like to explore all other options to achieve higher vibration criteria, like say that even 2000 nits with a mass timber floor. So to achieve those specific criteria, we need to have used all of these options to achieve those higher vibration criteria.
So, Sami, then what are the mitigation strategies in high vibration criteria mass timber floors? We talked a little bit about composite action. What are some of the tools we have in our toolbox?
So for mass timber building, as I mentioned, that it's a high frequency floor. So when we say high frequency floor, the frequency would be more than 10 hertz. So the response of the floor is governed by an impulse response. So every footstep is like an impulse to the floor structure. So that governs the response of the floor. Every event is an individual event. But in case of a low frequency floor, the response is governed by resonance of the floor. So one footstep can impact the performance of the floor even after 3 or 4 footsteps later. So it's the resonance build-up over time. So this is the distinct difference between a high frequency floor and the low frequency floor. So for low frequency floor, TMD or the tuned mass damper is a very efficient tool. But for high frequency floor, TMD is not very effective in this case. So to be effective, TMD, the floor frequency needs to be less than 8 hertz. But in mass timber floor, all the time the frequency is higher than 12 hertz. It could be even 18 hertz or 20 hertz. In some cases, we can use active mass damper, AMD, to control the motion of the floor. It actively senses the motion of the floor, and at the same time, it produces a signal that is opposite to the floor. So if the floor is deflecting downward, this device will generate a motion of the floor that is upward. So the net result is they will cancel each other out. The good balance of the floor frequency and the vibration performance can be achieved up to, say, 15 hertz. Anything above 15 hertz, AMD is also not very effective in controlling the motion. So here comes this effect of internal load-bearing wall or non-load-bearing wall, as well as exterior facade, that plays a significant role to control the motion of the floor. And at the same time, for the mass timber floor, we really want to place the corridor and the clear walking path within the column line. So that would be a very efficient tool to control the motion of the floor. And then find the right balance between the composite action and the CLT thickness. That's another tool to achieve higher vibration performance in terms of CLT. And in some cases, what we have done to add some secondary beam only for sensitive areas where the higher vibration performance is needed. So maybe 2 or 3 areas where we need 4,000 MIPS or 2,000 MIPS. Only at those areas we're going to have a different framing system, but other areas we will have lighter framing system. So it's a combination of stiffness, framing member layout. These are the parameters we can choose to control the motion of the floor for mass timber building.
What do you think are the steps that the industry needs to take to kind of catch up or create maybe a more uniform approach to vibrations and acoustics?
What I'm seeing in the industry that it's all the discipline like architectural and structural goes hand to hand for mass timber building. And at some point when the framing and everything is laid out, a vibration engineer starts looking at it, and then an acoustic engineer looks at it from an acoustic point of view. But for mass timber building, based on my past project experience, I see that this is all a collaborative effort. From the day one, acoustics and vibration need to be involved. And then even before laying out the framing system, vibration engineer might have a different aspect that needs to be incorporated. So this would make sure that down the road, we don't need to change the design significantly. All of these aspects of acoustics and vibration needs to go together, specifically for this mass timber building, as it's a new type of design that we are exploring still for at least acoustics and vibration. So this type of correlation and coordination from the day one is very important. And I think by combining those into early stage of design, this would make sure that our design and the performance as well as client expectation is met at the optimum economical cost.
Okay, Sammy. So what's next for vibration research in the field and kind of where do you see the future opportunities lie?
So for us, the next step would be tweaking our modeling parameters and design parameters so that we can effectively design mass timber for 2000 MIPS building assessment criteria. So we have confidence in designing those mass timber building up to 4000 MIPS, but we are pushing the boundaries to extend the capabilities up to 2000 MIPS so that mass timber building could be used all sorts of lab buildings. And this way, we can have a greener building construction and have a bigger impact in the industry.
Sammy, thanks so much for your insights today. It's a super interesting topic, and I can personally say that I've really enjoyed working with you and your team on a couple projects where you've helped get us to a finish line and a performance criteria that has made the client really, really happy. And thanks today for walking us through your work and for how you're shaping the next generation of high performance buildings. So thanks for joining us.
Thank you. Thank you for having me.
Kristina, good to see you today, and everybody. That's it for today. But join us again on our next Mass Timber podcast. We'll talk to you soon. Thanks a lot.
Tune in for our next episode, Greenbox, an innovative mass timber floor system. And like, subscribe, follow, or comment.